Okay, in this video, we're going to talk about power, electrical power. Just like energy is energy is energy, power is power is power. And so I'm going to use a light bulb to show this. So power is the rate at which we are using energy. And so if a light bulb has a lot of power, it's probably going to be brighter. So the brightness of the light bulb relates to the power. You will notice that when I turn the voltage up, the current goes up and the brightness goes up. So we can probably figure out that if brightness is related to power, when I turn the voltage up, if the brightness went up, that the voltage is probably related to power. And if the current went up, the current is probably related to power. And if I change my resistance and that brightness is changing because of resistance, the resistance is somehow related to power. Only we can see that with resistance, as resistance goes up, the brightness goes down, so we expect the power to go down. I am just going to straight up show you equations that are on your reference table. Let's do this. So your reference table tells you that power is equal to, well, let's think about this for a second. Let's write down all the units of stuff. We know that voltage is joules per coulomb. We know that current is a coulomb per second. Do you notice anything? Maybe if the units of power are joules per second, how can I get there? Easy, I multiply these two. If I multiply a joule per coulomb times a coulomb per second, the coulombs are going to cancel out. So it turns out that power will be voltage times current. So I can find power for anything by doing voltage times current. Turns out that we also know that, for instance, current is V over R. So what if I replaced I with V over R? Well, then I would get V times V over R, which would be V squared over R. Turns out V is equal to I²R. So what if I replaced V with I²R? I would get I²R. So all of these will give you power. So if you know the voltage going through something and the current going through it, you know the power it dissipates. If you know the voltage going through it and its resistance, you know the power it dissipates. If you know the current going through it and the resistance, you know the power it dissipates. The power of the entire circuit has to add up. So if you did the total voltage and the total current, then each of the individual powers of every little resistor would have to add up to the total, right? Because conservation of energy. Let's just quickly do, what if I wanted to know the energy in the circuit? I think they probably do W, but we know that power is maybe work over time. So if I were to rearrange it, work would be power times time. So if I wanted to know the amount of energy being used, I would simply multiply any of these things times time. So work is power times time, which would be VI times T, which would be V squared over R times T, which would be I²R times T. So any of these things times time will give you the work, because if I have a joule per second and I multiply by a second, I will be left with a joule. Let's just quickly look at a little example, and then we'll look at, and actually that's it, right? So let's say I want to know, let's do 2 resistors just to show. Resistor 2. Let's make them different amounts of resistance. Let's make this one 10 ohms. Let's make this one 20 ohms. And let's make this a 30 volt battery. So that numbers might look nice. All right, here we go. So first of all, what should we do? We should take our total information and find what we can. So I know that my total voltage is 30 volts. And by the way, I'll draw this on the board and we'll solve it. So I've got my battery, I've got resistor, I've got resistor, I've got a 10 ohm resistor, a 20 ohm resistor. We'll call this R1, we'll call this R2, and our voltage is 30 volts. Okay, well, let's start by finding R total because it's a series circuit and that's easy. R total will be R1 plus R2, which will be 10 ohm plus 20 ohm, which will be 30 ohm. So our R total is 30 ohms. Okay. Now that I know R total and V total, I can find I total. So I total will be V over R, total, which will be 30 volts divided by 30 ohms, which will be 1 amp. Easy. So now I know that I total is 1 amp. Now the question is, what's the total power dissipated by this circuit? Well, there's more than one way to do it, but power total will be V squared over R, it will be I²R, it will be VI. Pick one. You have the means to solve all of them. I'm going to do, I don't know, VI. So I'm going to do 30 volts times 1 amp, which will be 30 volt amps, which is 100% correct, which would be 30 joules per second, which would be 100% correct, which would be 30 watts, which is 100% correct. So now I know that power total equals 30 watts. What if the question was how much power goes through R2? How much power does R2 dissipate? Well, then I put in the information for R2. Power through 2 equals, what are the things I know about R2? I know that its current is 1 amp because it's a series circuit. And I know its resistance. I don't know its voltage right now. I did not measure the voltage drop on R2. Could I measure the voltage drop? Absolutely. Could I calculate the voltage drop, I mean? Yeah, I could calculate the voltage drop. Don't remember how to do it? Let's do it real quick. If I took a voltmeter and I wanted to know the voltage going across R2, I'd plug in the information for 2. So I want to know the voltage on 2. So it will be I²R2. 1 amp times 20 ohms means that the voltage drop is 20 volts. So this one is getting 20 volts right now. So again, I have more than one way to solve it. Let's do power 2 equals I²R to 2. So I know 1 amp squared times 20 ohms. And what do you know? It's got 20 watts. If this one has 20 watts, I bet that one has 10 watts because the total has to add up to 30 watts. All right, let's quickly look how this might be different. So in a series circuit, the larger resistor, how do I put this? In a series circuit, the larger resistor had more power, okay? Because in series, they both had the same I, but one of them had a larger resistance. Now, for the entire circuit, let's quickly look at this. Power total equals I²R, total. If the resistance of the entire circuit goes up, the power of that circuit's going to go down. So if I add more resistors in series, the total power is going to go down because the current's going to get slower and slower and slower and slower. So even though it looks like as resistance goes up, it's not true. Because as the resistance goes up, the current goes down, and this squared is a bigger thing. So what might be a better thing to look at here? Ah, this is a much better picture. My voltage isn't changing, right? So I chose maybe a 30-volt battery. As my resistance gets larger and larger and larger, I'm dividing by a bigger and bigger and bigger number, so my total power will go down. Now parallel circuits are a little bit different. Every time I add something new in parallel, I increase my current, right? So I've got my battery. No matter what, if I add a new resistor, no matter how big that resistor is, the current, the total current gets more and more and more because I have more paths to take. And every time I have more paths to take, more current's going to flow. So the total amount of current and the total amount of power for this circuit goes up as I add more and more and more ways for the current to travel. Let's just do a very simple picture. Let's do the same 30 volts. Let's do a same 10 amp or 10 ohm and a same 20 ohm. And again, let's call this R1. Let's call this R2. This time, how do I go about this? Well, first I have to find Req. 1 over Req equals 1 over R1 plus 1 over R2. So I've got 1 over 20 ohm, 1 over 10 ohm is R1, plus 1 over 20 ohm is R2. I have to find a common denominator, so 2 over 20 ohm plus 1 over 20 ohm, so 3 over 20 ohm. So 1 over Req equals 3 over 20 ohm. That means Req equals 20 ohms over 3, which we know is 6.67. So the total resistance of this thing is 6.67. Req, 6.67 ohms. Okay, now I find maybe the total current. By the way, this is to find the total right now. I'm looking for total stuff. We'll see a different way we can do this. I total will be V total over R total. I total will be 30 volts over 6.67 ohms. And what did we determine that was? 4.5 amps, okay. So, we now know Req, 6.67 ohms. We now know I total, 4.5 amps, and we know V total is 30 volts. What can we do with this information? We can find total power. Power total. I don't know, let's use VI. I don't really care. So we use 4.5 amps times 30 volts, and we get 135 watts. 135 watts. So the power total is 135 watts. Okay. Well, let's look at individual information. Oh, that's not cool. Let's look at individual pieces of information now. I'll keep over here that power total was 135 watts, and now let's check something. Let's find the power on just each of these. Hey, really easy. I know the voltage on this one has to be 30 volts because my reference table tells me that in parallel, these get the same voltage. Cool. So power 1 will be V1, R1. I know both of those things. 30 volts times 10 ohms. Why did I write V1, R1? Because I don't have kids to tell me when I do stuff wrong. Power 1 equals V squared over R of 1 and 1, which is 30 volts over 10 ohms. And don't forget to square those volts, right? So 30 times 30, 900. 900 divided by 10, 90. So power 1 is 90 watts. Power 2, V squared 2 over R2, which will be 30 volts squared, don't forget your parentheses, over 20 ohms. 30 times 30, 900. 900 divided by 20, 45. 45 watts. Hey, what's 90 watts plus 45 watts? It's 135 watts. It all works out. What do you know?